Gravity is one of the most interesting and yet common forces in the universe. It's so familiar that we can often forget it's there. Though it might seem simple, gravity governs many of the motions throughout the universe, from objects falling down on Earth to the motions of planets and satellites, and even the formation of stars and entire galaxies. But how does it work? What exactly is gravity? In this video, we'll be going back through history to see how our understanding of gravity has changed over time, and challenge you to solve some example scenarios to test your understanding. Let's get started. The physical effects of gravity are easy to observe. It holds us to the ground, objects fall when thrown, rain falls from the sky, etc. Ancient philosophers observed these same motions and attempted to come up with some explanations. One Greek philosopher, Aristotle, dominated the understanding of motion for almost 1800 years. He claimed three things about the world. The first being that objects move toward their natural place in the universe, and that heavy bodies or objects fall toward Earth's center because of their innate gravitas, or heaviness. This might imply that heavy objects fall faster than lighter ones. He also thought that motion cannot occur without a cause or source, suggesting that a constant force creates uniform motion, and then an object that slows or comes to rest does so because no force is acting on it. It simply reached its natural place. Finally, Aristotle claimed that the heavens are distinct, perfect, and unchanging, just like clockwork, suggesting that different laws of nature apply to the realm of the planets and the stars than ours here on Earth. In the 1600s, an astronomer and physicist named Galileo studied motion by performing various experiments, something that Aristotle never bothered with. Galileo sought to describe motion as a relationship between speed, distance, and time. He studied falling objects to understand how their speed changed as they fell towards Earth. However, objects fell too quickly for him to time accurately, so he used a series of inclined planes of different angles to effectively slow the acceleration. He rolled metal balls of different masses down the ramps, measuring the distances they traveled each second. What do you think he discovered about the motion of the different balls as they rolled down the ramp? Galileo had found that the balls traveled a larger distance down the ramp every second, and had the same acceleration rate despite their difference in mass. His experiments also revealed the concept of inertia, that objects will resist a change in their motion. He imagined a second ramp opposite the first, at the same angle. A ball dropped would go up to the same height on the other ramp without friction. If you extended and lowered the second ramp, the ball would reach the same height but travel just a little further. Galileo realized that if the ramp was lowered to be horizontal, the balls would continue with the velocity they had gained, moving uniformly without a force applying the motion, contrary to what Aristotle had claimed. In addition, Galileo made a number of astronomical observations using the newly invented telescope. In particular, he discovered moons around Jupiter and observed their orbits around the planet. The idea that celestial bodies could orbit something other than Earth was a direct challenge to the current model of the universe. Galileo's new understanding of motion, as well as his observations of celestial bodies, would eventually help revolutionize modern science. Thousands of years before Galileo first used the telescope, ancient philosophers also observed the motions of the heavens and attempted to come up with a model to describe what they believed was our universe. We now know this was just our solar system. The actual universe is much more vast than anyone at the time could have imagined. In Greek astronomy, Aristotle popularized the belief that the Earth was at the center of our universe, with the planets, the sun, and the stars orbiting on perfect concentric spheres. However, astronomers observed a bizarre motion of some of the planets. The planets typically traveled eastward across the night sky, but Mars would periodically appear to stop and move backwards for a period of time, looping around before continuing on its regular course. They called this retrograde motion. In the year 150 CE, another Greek astronomer named Ptolemy devised a geocentric model that explained this motion using circles on top of circles, called epicycles. Mars orbited a point in space that in turn orbited the Earth in uniform circular motion, resulting in a path tracing Mars's retrograde motion. While not very elegant, Ptolemy's model kept Earth at the center of the universe and could predict the positions of the planets with sufficient accuracy. Similar to Aristotle's theories, Ptolemy's geocentric model dominated the understanding of planetary motion for more than a millennium. Around 1500 CE, Nicholas Copernicus was the first to develop a heliocentric model of the solar system, with the Sun at the center. His model explained retrograde motion in a simpler way, as a perception illusion caused by the Earth overtaking Mars in its orbit. However, his model wasn't any more accurate than Ptolemy's, still requiring epicycles to predict planetary positions. Today, we know that the Sun is at the center of the solar system, so why didn't his model work? Why was Copernicus's model just as inaccurate as Ptolemy's? Both still believed that celestial bodies needed to move in uniform circular orbits, but what if they didn't? Enter Johannes Kepler in the 1600s. Kepler had worked for his late predecessor, Tycho Brahe. Tycho had collected a large amount of incredibly accurate observational data on stellar and planetary motions, but couldn't explain them using any existing system or create his own. After years of poring over and calculating Tycho's data, Kepler found the answer. Planets orbited not in circles, but in ellipses, with the Sun at one focus. This became the first of Kepler's 3 laws of planetary motion. The second law showed that planetary motion wasn't uniform, with planets orbiting faster as their orbital paths neared the Sun. With his third law, he found that a planet's orbital period increased with its distance from the Sun in a specific way. The work of Galileo and Kepler had revolutionized and redefined our understanding of both motion and planetary motion, respectively. But neither could answer why things moved according to the rules they had discovered. The source of their motion remained a mystery for about another 50 years, when Sir Isaac Newton finally found the connection. According to legend, Newton witnessed an apple fall to the ground from an apple tree near his home. He realized that the force that caused the apple, as well as every other object, to fall towards the Earth could be the same force that kept the moon in orbit and governed all of planetary motion. From this idea, Newton developed the first true understanding of gravity, finally unifying the physics of the heavens and of the Earth into one universe. Newton proceeded to develop and quantify the surprisingly simple laws that govern motion and gravity. But before we dive into each of Newton's laws, we need to discuss the elements of motion with a little more detail. From Galileo, we know that speed is defined as the distance traveled per unit of time. Velocity is a little more specific. It is the speed of an object in a certain direction. In other words, it is the rate at which the position of an object changes. Galileo then said that acceleration is the change in velocity over time. Lastly, a force is any effect that changes an object's motion. Quick experiment. Imagine that a car traveling at 40 miles per hour begins to turn without changing its speed. Is the car accelerating? Yes, it is. Since velocity depends on speed and direction, a change in direction is still considered an acceleration, even if the speed doesn't change. Now we're ready to discuss Newton's laws of motion. The first law deals with Galileo's concept of inertia, and says that objects at rest will stay at rest, and that objects in motion will stay in motion with constant velocity unless acted on by an external, unbalanced force. If the total forces acting on an object cancel out, we say that the object is in equilibrium, and it'll just keep on doing whatever it was doing. His second law deals with forces and acceleration. It says that a force exerted on a mass will result in the acceleration of that mass. The amount of the acceleration depends on the amount of force and the mass of the object. Newton quantified this relationship with the formula A equals F over m, which you might know by the more familiar F equals ma. or force equals mass times acceleration. As we discussed earlier, this also applies with circular motion, as an acceleration can be a change in direction as well. Newton's third law says that for every force on an object, there is an equal and opposite reaction force on the source of the initial force. For example, if one astronaut floating in space pushes his friend, both astronauts will move away from each other. This law was vital to understanding how gravity and forces in general behaved in systems. Let's look at a falling object, like Newton's apple, and apply what we've learned. As it's dropped, the apple accelerates from rest toward the Earth at a constant rate, traveling further and faster each second. Newton understood that the Earth must be exerting a gravitational force on the apple, causing it to accelerate toward the center of the Earth. But what was the value of that force and acceleration? Newton formulated the universal law of gravitation to explain how masses interacted with one another. Every mass in the universe attracts every other mass through a force, what we call gravity. So, imagine two masses in space, separated by a distance, both experiencing the same gravitational force towards each other. The amount of the gravitational force is directly related to the product of the two masses. What do you think will happen if we double the mass of one of the objects? This is exactly what we see. Larger masses exert a greater gravitational force. However, remember that this force is the same for both objects, as per Newton's third law. But what about distance? Let's go back to the original scenario, with equal masses. If we double their distance, what do you think will happen? Newton realized that gravity follows an inverse square law, meaning the force due to gravity is inversely proportional to the square of the distance between the centers of each mass. This means that as the masses move farther from each other, the force gets increasingly weaker. Together, these relationships gave us the universal formula for gravitation. The force between two masses due to gravity is equal to the product of both masses divided by the square of the distance between their centers. This amount was then multiplied by some gravitational constant, which was found later in experiments to be around 6.67 times 10 to the negative 11th. You can ignore the units, they're going to cancel out, but just note how incredibly small this value is. For something so important, gravity is significantly weaker than all the other fundamental forces in physics. Back to our falling apple. Using Newton's law of gravitation, we can finally understand and calculate what's happening to objects as they fall. As before, we know that the gravitational force of the Earth on the apple causes an acceleration. We also now know the formula for the force of gravity between the objects. Using algebra, we see that the mass of the apple doesn't matter. This is why Galileo observed that the acceleration due to gravity is the same for all objects near Earth's surface, depending only on the mass of the Earth and its radius. We label this acceleration as lowercase g, and it has an average value of negative 9.8 meters per second squared. The negative just means towards the Earth's center. So if gravity is the attractive force that pulls matter together, and it governs all of the falling objects here on Earth, why doesn't the Moon or International Space Station or any other satellite for that matter fall down and crash? There's a common misconception that there is no gravity in space due to the apparent weightlessness we observe in videos and movies of space travel. In reality, everything that orbits the Earth is constantly falling towards it. Astronauts experience weightlessness because of this constant state of freefall. They don't fall to Earth because, contrary to what we can see, they're moving incredibly fast. Imagine you drop a ball from a really high tower. It would fall directly towards Earth, accelerating just as any other object does. Now imagine you launch that object horizontally. It would still fall towards Earth, but it would travel some distance along its surface first. If you keep increasing the speed of the ball, it will travel farther and farther. Newton realized that if the speed was great enough, eventually the ball would fall around the Earth instead of into it, with gravity pulling its trajectory the entire time. For a stable low Earth orbit, that speed is about 7.8 kilometers per second, or 17,000 miles per hour. Any slower, and eventually the ball would re-enter the atmosphere. If there wasn't any gravity in space, the ball would just fly off in a straight line, based on Newton's first law. Kepler's laws of planetary motion were accepted as true due to their sustained accuracy over many years, but scientists couldn't initially explain where they came from or why they worked. Using his laws of motion, gravity, and some calculus, Newton derived the very relationships that Kepler observed, suggesting that the physical laws we see here on Earth are the same throughout the universe. So that's all there is to gravity, right? Wrong. Newton's discoveries transformed our understanding of our physical world and the cosmos, and would go unchallenged for nearly 200 years. But there are still phenomena his laws couldn't address. Newton couldn't understand how masses could interact via gravity over immense distances, seemingly connected by a mysterious and invisible force. He had figured out the laws that govern the motion, but did not understand the mechanism behind it. Predictions based on his equations also weren't perfect. In the 19th century, observations of Mercury's orbit around the Sun showed that it was changing slightly over time. This was predicted by Newton's laws, suggesting that the gravitational influence of the other planets would cause orbits to precess, or advance over time. However, careful analysis showed that the Newtonian effects alone couldn't account for the precession rate. The orbit was changing faster than expected. Albert Einstein answered both of these questions and more in 1915 with his theory of general relativity. The thought experiments and calculations involved are far too complex for this video, but the basic ideas are these. Space and time, originally thought to be separate, are actually intertwined, creating a sort of fabric of the universe called spacetime. Einstein said that the presence of matter curves spacetime. The more mass there is, the greater the curvature. A star's large mass creates a sort of gravity well, curving spacetime near it. In this view, gravity isn't a force like Newton thought, but simply a result of the curved geometry of spacetime. Objects don't experience a mysterious force at a distance, they simply follow the shortest straight line path through a curved space. This results in an acceleration, or what we know as gravity. There are many consequences of general relativity. Too complex to describe in detail here, but there are two that are really unique. Black holes and gravitational waves. Black holes are incredibly dense regions of spacetime, made from the most massive of stars collapsing at the end of their life cycles. Their mass warps spacetime so strongly and across such small distances that their gravitational wells are practically infinitely deep, to a point where nothing, not even light, can escape. This is why they're called black holes. They're almost impossible to observe directly, and therefore are some of the most exotic and mysterious regions of the universe. If matter can warp spacetime, what happens when massive objects move through it? As objects move, they actually drag spacetime along with it, like waves in the wake of a boat. These waves require violent activity of some of the densest objects in the universe in order to form, such as black holes. Imagine what might happen if two massive black holes suddenly collide. Spacetime would ripple out in all directions, just as dropping a rock in a pond would cause ripples along its surface. These gravitational waves were predicted by Einstein in 1916, and it took 100 years before we could first detect their existence. In the future, they could act almost like a new sense that we can use to view the universe, allowing us to feel the vibrations of gravity. Gravity is everywhere. Through thousands of years of observations and study, we now know that it's a vital part of the very fabric of our universe. We hope this video has taught you a little bit more about what we know about gravity today and its far-reaching implications and importance, from everyday interactions here on Earth to creating and guiding the evolution of the universe itself.